for inviting me, and thanks for coming. So there will be 4 talks, each for 1 hour. And so the topic is about Teichmueller dynamics, and more generally also about the geometry of modular space of curves. There will be some interaction between several different fields, like average geometry, complex geometry, and a little bit combinatorics and dynamics. So I guess some of you have different backgrounds, like in different years. So we have enough time. So whenever you have a question, just feel free to let me know. So in the first lecture today, so let's introduce the basic objects we are going to study. So I wrote down 2 terms in the title, translation surfaces and holomorphic forms. So I'm going to give you the definition. And indeed, they look like 2 different names, but they define essentially the same object. So let's start from the first one, translation surface. So I'll define the definition. So the first definition for translation surface . So sometimes people also call it the flat surface. And the meaning why it's called flat will become clear. So maybe definition number 1. So first, let's take X. So a closed, like a real 2-dimensional topological surface. Topological. So let's take a finite set of points in X called sigma. Here's sigma. It's a finite. So if X along with sigma satisfies the following conditions, which I'm going to define, then we call X a translation surface. And what are the conditions? So I'm still continuing this definition. So if, there exist, first of all, translation surfaces are defined over a Riemann surface. So here I only give you a topological surface X, so I have to define its complex structure. So which we can define, for instance, by using like atlas of charts. If I decompose X into open subset, for each open subset, I can associate some like a coordinate, and I only need to describe the transition functions between the coordinates, right? So that's one way to define a structure. So first, I'd like to define it away from sigma. So if there exists a special atlas of chart, from the complement of this finite set sigma, so that is the complement of sigma in X to the standard complex plane, the Euclidean plane. That's denoted by C. So C is a standard Euclidean plane. Such that so first of all, so I might have 2 charts in X. The complement of sigma in X mapping to C is the overlap, so I have to define the transition function. First of all, the transition functions associated to this chart are all given by of type translation. So I'll explain in a second. What does this mean? So that is, suppose I have two charts and they overlap. Maybe for this chart, maybe let me put it this way. Suppose here is in this open subset X, and here for this part I associate to some coordinates given by Z lying in the Euclidean plane. This part is Z, and for the other one is some Z prime. And because they overlap, I have to define the transition function associate the relation between Z and Z prime. So the transition functions are always look like the following. So Z prime is equal to Z plus some number. It's not like some fancy function just given by translation. Translation just means parallel translation plus some constant. I mean, this constant, it could vary if you take different charts in the same system. However, I'm just saying the transition functions of this type. Okay. So this is the first condition. And secondly, what happens around these finite many special points in the set sigma? So secondly, so look, so here I pick this complex plane C, not only with a complex structure. I specified you should treat it as a Euclidean plane. Euclidean plane contains some more information. It has a standard like horizontal and vertical coordinates, x, y coordinate. That makes it looks like it's just this blackboard flat. So that's sort of partially illustrate the other name why I call it flat. So this Euclidean plane really has a flat structure given by the standard x, y coordinate. So it's like this. And in this way, I mean, because we use coordinate from the Euclidean plane, you can measure, in some sense, the angle around the point. For instance, if I take an ordinary point here, in the Euclidean plane, then around it, if you draw a small loop and look at the total angle, it's just given by everywhere by 2 pi. Right, like that. However, for those special points, we require them to be not necessarily 2 pi, but some integer multiple of 2 pi. I'll draw some picture to explain, but let me write it briefly as follows. So for each special point P in this finite set sigma, so roughly speaking, so the angle, so I'll make it more precise at P, induced under the Euclidean metric or the probect Euclidean metric is some integer multiple of 2 pi. Let's write it k times 2 pi, where k can be any positive integer. So this is sort of a rough definition. It's not so precise, but let me explain more precisely what this means for the second point. So more precisely, so around this point P, it looks like so the local neighborhood of P in X is really arithmetically given by the following gluing of some disks P. So it looks like P. So it is glued by so 2k plus 2 half disks asymmetrically. So what does this mean? So let me explain. So let's just work out one example to make sure it is very concrete. So let me do the case for k equal to 2. So suppose I pick this integer multiple to be 2 times 2 pi. Okay, so then it's not quite like a 2 pi. 2 pi you should think of as just like an ordinary point in the Euclidean plane. Suppose it now is 2 times 2 pi. According to this definition, I need to glue 6 half disks. So let's draw 6 half disks. One of them got 4 of them. Sorry. And so you should consider this boundary just give you the local neighborhood of P, and P sits at the center of these disks. So how do we glue them together? So each half disks, so it has like 2 boundary rays given by the 2 radian. So let's mark them. This is A1, this is A2, A1, A2. I glue this A2 again, so I really want to preserve this translation structure away from the center point. So I glue this A2 to this part. They are like parallel and of the same length, so I can describe the gluing by translation. So I mark this by A2. That means, so when you go from some interior point to hit A2, you should consider now the paths continue on the same point on the other A2 and continue. And let's mark the other one by A3 here in the second disk. This A3, let's glue it to this A3 because these 2 parts are parallel and of the same length. And suppose the other part is A4, we glue this A4 to this A4. And this, let's label it by A5, and this A5 is identified with this A5. And here is A6, and this A6, A6. And finally, to close up, so we get A1, A1 on the back. And it's maybe also help if you can imagine this gluing in your mind, or try to glue them together and form a sort of a more global picture. It goes like, so maybe global you should think of is really something like this. And 6 half disks altogether, like 3 whole disks. But you go this way, this way, this way, and eventually you can't come back. And after these identifications, all the 6 centers are glued to be the same point. So let's call it P. So in this case, so the total angle at P for each half disk, you get pi. You have 6 of them. So the total angle at P is given by 6 pi. That is 3 times 2 pi. So this is an example when k equal to 2. Sorry, k equal to maybe 3. Sorry. Okay, sorry. And in general, for any positive integer k, you can proceed in the same way. Just draw more copies of disk. But this identification, you see the pattern. And the thing is, well, in this picture, although it looks quite bizarre, the only bizarre point is still this point P. Away from P, everywhere else, you still have this flat geometry looking like a Euclidean plane. And let's give those point parameters in sigma, this special point P, let's give them a name. So let's continue 3. So these points in sigma are called saddle points. And if P in sigma under this description has total angle, say 2 pi times k, we see that yeah, just well, I'll do this later.
K3, then we need 8 half in
Oh, in this case, k equals 3, actually I have, because here I just described in the case of 3 times 2 pi, so I need like 6 half disks. So this example is really, I should also modify this, is 2k half plane. Because sometimes you will see in the next definition when I describe one forms, so there's a just like shift by 1. So in terms of this flat geometry language, the cone angle you get 2 pi times k, but in terms of one form you get some one order k minus 1. So this will becomes clear. So it's like if you have a function like z to the kth, you differentiate, it becomes like k minus 1 dz. And so the one order decreased by 1. And maybe a better way to think about this picture, just for those of you who know like Riemann surfaces branch covers. So this picture should remind you, so locally around that point P, the flat metric is really induced by, in this case, a branch cover totally of degree 3 locally around P with like total ramification. So you should think of this locally, give you a covering. Suppose this center point is P somewhere. So the map is given by Z mapping to Z cube. And here you have a standard Euclidean metric, you pull it back. That realizes the local flat geometry around this special point P.
So does it have something to do with OB form?
So far, not yet. Yeah. Yeah, it has something to do with what I'm going to tell you next about one forms. Yeah. So this definition, the first definition, just describes again a Riemann surface along with the additional structure which looks like a flat, or in other words, you can describe away from these finite special points, all the transition functions are given by translations. Yeah, so far has nothing to do with OB form. Any other questions? Okay, let's proceed to the next equivalent definition, holomorphic one forms. That's very simple. So a translation surface is really nothing but a holomorphic one form. It's just I'll explain why this makes sense. Let's call it omega on the surface X. So with the only constraint or the condition we impose to omega is that this omega is not identically 0. If you have everywhere 0 one form, you lose everything. So let's just consider omega is, it might have isolated zeros, but not identically 0. Omega is not identically 0. Okay. That's it. So the second definition is very short. Well, you must be, I guess, confused. So the two definitions are very different. Why are they equivalent? So let me try to explain. Well, the way we do it, we do it on two directions, right? First, suppose we use the first definition to describe a translation surface, and then how do we derive a one form out of a given translation surface, right? And conversely, suppose you give me a one form, I have to tell you how to define the translation surface in the first definition, how to describe the sigma and the special cone angles around each special point. So let's do in the first direction, given the translation surface, let's read off a one form. So from translation surfaces to one forms. So rather just do it in an example. I mean, the general way to do it will become clear after you see this example. So let me just draw a very concrete translation surface as a plane polygon identifying some edges. Then we will determine one form out of it. Okay. Okay, so I use 4 colors to draw actually an octagon with 8 edges. But the way I drew it, so I decompose the 8 edges into 4 pairs, right? So each pair consists of 2 edges labeled by the same color. So the reason is that for the 2 edges with the same color, you identify them. You see the way I drew this white one, that white one. They are basically the same vector, only up to shift. Shift just means translation. And this yellow one, that yellow one, they are also the same vector, just by shift. Now what you do, you call this surface X, bounded by these edges, and you identify the pairs of edges labeled by the same color. And after this gluing, you will get a closed surface, right? At least it's closed up. And so let's first work out, so even as a topological genus, topological surface, what is the genus of this surface? So glue the edges with the same color by parallel translation, So X is a closed surface. So what is the genus of X? Let's see. So can anybody quickly compute it?
2.
Why is it 2?
Because there's only one vertex.
Okay, and so I guess you apply the topological Euler characteristic to compute it. The genus indeed is 2. So let's just go over, I guess, the reasoning you pointed out. So, well, yes. So let's start from this vertex. Let's call it P, because I keep using P. So because this white one, that white one are glued together, so this point has to be P as well, right? Because they are glued. And this yellow one, that yellow one, they are identified. So this point is P, that point has to be P as well. So this red one, so this is P. And this blue one, so here is P. And then white, P. And you can see the pattern. So everywhere, all the vertices are the same point after identification. Let's label all of them by P. Okay. Then, well, in this decomposition, this tells us the surface X now has one vertex P and 4 edges, right? 8 edges, but indeed there are only 4 because they are identified in pairs. That is like 1 vertex, 4 edges, and 1 2-dimensional face, right? Just given by this face. And this tells us, so 2 times, or 2 minus 2g, let me write it here, equals, so V naught 1 minus 4 plus 1. So this tells us the genus indeed is equal to 2. Right. So we got a genus 2 surface. This is good. So we have determined the genus of X. But we need more information. So secondly, so we can also define this atlas of charts away from P, because at any point, well, if you take an interior point in X, because this interior is embedded in the Euclidean plane, you can just use a standard Euclidean plane coordinate Z to be your coordinate, right? So let's take a point on the edge, but not P. So let's take this point. and drawn a small open subset around it. Suppose you use the standard Euclidean plane coordinate, let's call it z, and you take the same point because you glue them together and take the same neighborhood on the surface x. So, but there are two different subsets in the Euclidean plane, right? So the coordinate there actually is different, it's z prime, right? But what is the transition function between them? Well, we identify these two under translation. So the transition function is given by translation. So here, so z prime is really z plus some constant determined by the amount of shifting from z prime to z, right? Well, I mean, we are very close to, indeed, from here you can see why we can get a one form. So how to get rid of the constant, you take the derivative, you differentiate. So it tells us, although globally these coordinates z prime, they are not globally defined. So these two correspond to the same points in x, but they are with different functions. If you differentiate, the one form is globally defined. So you can differentiate terms. Omega equal to dz is globally defined. So first, so it's defined on x away from p, but there's only like one, like a isolated point p. You can apply sort of extension theorem to show you can extend it uniquely to be holomorphic again on the entire Riemann surface. So this is very nice. So we have this flat structure, you differentiate these coordinates, you just get one form omega you want. But we are not done yet, so let's try to take a closer look at the geometry of p. Because remember, in the first definition, at this point p, there is some like information about the total angle, like some integer multiple of 2 pi. So here, let's describe this integer multiple. So at p, so now things is very concrete. So we can count the angle. So how to count? We just add them up, right? So the total angle is, there should be some high school geometry. we are in the octagon, so the total angle of the 8 vertices should be is 6, right? It's 6 pi. And 6 pi is 3 times 2 pi. So this satisfies the condition in the definition. We do get integer multiple of 2 pi. And moreover, we can look at the information of this one from omega. So what is omega? So it tells us if you have 6 pi, that is 3 times 2 pi. If you still remember the picture I erased about this kind of local branch cover description for this special point p, that means, so locally at p, because you have 3 times 2 pi, 3 tells you the local should be something like a z cube. But now we are looking at a one form. One form should be differentiating of this z cube. So look at p, omega should be given by up to some non-zero scalar, so d of z cube. So where z3 comes from this integer multiple. And if you differentiate, this is, again, so up to this constant 3 is z squared dz, because for the information of a one form, we try to determine the vanishing order of this one form at its 0 point. So this tells us, in this case, so omega has a double zero at p. So this exponent tells us p is a 0 of omega with vanishing order equal to 2. And this also satisfies, for instance, the degree of the canonical unbounded if you prefer, or the Gauss-Bonnet formula, because for genes 2, so from the one form, on the genes 2 surface, the total degree of a zeros counting with multiplicity should be given by 2g minus 2. In this case, it is true. And you see clearly in this picture, only p can be possibly a 0 of omega. Everywhere else is not. It's just given by dz, it's not 0, right? So this example, I hope, just illustrates the following general conclusion. So let me write down. Let me start from here. So we can give more detailed information, at least in this case. So if, let me use this symbol, omega parentheses 0, to denote the zero loci of omega along with their vanishing multiplicity. So let me write it this way. So M1, P1 plus up to M n Pn. So that is, so these coefficients Mi are positive integers, and the Pi's are distinct points in the surface X. So this just means this one form omega has n distinct points given by P1 up to Pn. For each Pi, the vanishing order of omega at Pi is given by Mi. Right. So then, just illustrated by that example, at each Pi, so omega looks like, well, what do we mean by vanishing order given by M? That is Z to the M's dz, right? So where this M is Mi in this notation, the coefficient of Pi. And if you have this, so again up to Mi plus 1, this non-zero scalar, this is coming from d of Z Mi plus 1, right? So this is just a generalization on a general case of a special situation in this example. So this tells us if you have Z to this order, so locally at this point Pi, you have to glue how many disks? Mi plus 1 disks. For each Z, you glue 1 disk, but you have Mi plus 1, so you get this many. This quickly tells us the total angle under this flat metric at Pi is given by this integer multiple times 2 pi, so Mi plus 1 times 2 pi. So that's also why in the first definition I was a little hesitating, use k or k plus 1. So because here shift by 1, just because when you differentiate, you have to bring down 1. So here Mi becomes, in the function case, Mi plus 1. Any questions? Okay, so this is one direction of this relation between translation surface and one form. Let's go backwards. Conversely, suppose you give me a one form of this type. So how do we construct a translation surface? Right. Well, we just need to reverse what we did before. So originally, in the other direction, in order to obtain this one form, we take the transition function and we differentiate. We take the charts z and z prime, we differentiate. Now, if you want to go backwards, just need to integrate. You start from this one form omega, you integrate, right? So simply speaking, this is nothing but reversing what we did, but integrating your local coordinates. So maybe let me write it here. So suppose given omega of one form on X of that type on the Riemann surface X such that the zero of omega is of this type M1 P1 plus Mn Pn. Okay. So you integrate So give the a system of coordinates in the first definition. So all we need to check is that, so if you integrate omega, you obtain this coordinate functions. So what are the transition functions between them? Well, the thing is, suppose you have, like, say, two different integrals. Omega is something like say 1, and you have another one, maybe z and z prime. I mean, you take antiderivatives, antiderivatives, they only differ. They're not unique, but they differ by a constant, right? So that tells you z prime is nothing but z plus some constant. So the transition functions are, you have to make sure when you integrate, and they are away from the zeros of omega to make sure this is okay, and independent of the integration. And at each special point pi, so again, so the information is already, I wrote it here. So because omega locally looks like z to the mi, let me just write down one more time, dz, that is d z mi plus 1. That really tells us, I'll just repeat what I wrote down there. So the angle at pi. So pi is a saddle point in the first definition with angle given by mi plus 1 times 2 pi. In other words, so the finite set sigma in the first definition of transition surfaces really correspond to the set of zeros of omega. And the angle information, this integer multiple, is the vanishing order of omega at p plus 1. So let me present a couple more examples just to illustrate this idea, especially in low genus. So we saw an example of genus 2. So some examples, let me rename it. This is now example 1. This is genus 2 with a double zero. Omega has a double zero at p. Okay. Let's do another simple example. Let me do it with genus 1. Well, in the case of genus 1, which is a torus, right, or elliptic curve. So every holomorphic one form is everywhere non-zero, is not vanishing at all. That tells us every point, if you present it under this flat geometry picture, you should not see any special point. So let's do it. And also, you must have seen this picture many times if you learned basic Riemann surfaces and geometry theory. So from the genus 1 Riemann surface, the way to present it is draw a plane polygon and identify the two parallel edges. So you can do it this way. That's it. Although it looks like in this way, so the vertex is a special point. However, if you glue it together, the vertex, the total angle for the parallelogram is still 2 pi. It's nothing special. Indeed, you can cut and repaste this parallelogram. Then this vertex just becomes interior point. So everywhere, this is really a flat torus. If you glue them together, it looks like something like this, right? And you should think of somehow there's like a, you do have this line looks straight, it becomes some straight line going around. But that's okay. So in this case, just genus 1, no zero. The one form has no zero. Okay. So genus 1 is kind of simple. Well, let's move back to genus 2, but do a more complex picture. Because here I have a special case of double zero. So how about you prefer a genus 2 surface with a one form that has two simple zeros? So let's also do that case. So in this case, I want to do a genus 2 surface, and omega is one form with 2 simple zero. Simple zero just means vanishing order equal to 1. Well, I can do the following. So now I don't have enough color chalk, but let me just draw in the same color, but label the edges. Do this later. Okay. All right. Well, this looks like a bizarre polygon. If you count the total number of edges, there are in total 10 edges. But again, I decompose into 5 pairs labeled by A, B, C, D, E. So A and A, these 2 edges, they are still the same vector. And B and B, they glue together, C, C, D, D, E, E. But in this case, let's do this vertex game. Try to count after identification what are the different vertices. So let's start from maybe this one. Let's call it. Call it P. Maybe call it P1 here. And E, so this point is P1. And D with D, so this point is P1. C and C, so this point is P1. And B with B, this point is P1. Finally, A and A, you get P1. So it doesn't really mess up with the other unlabeled vertices yet. And similarly, if you do P2 here, so A and A, this becomes P2. And D, this is P2. C with C, this is P2. And E, this is P2. I think we are all done. So the 10 vertices after this identification, they again break into 2 groups, each consisting of 5 vertices identified at the same point, P1 and P2. So this already tells us, in this picture, suppose you look at the corresponding one form omega, it has 2 special points, P1 and P2. They are different, even after gluing. So what are the angle information? Because that's what tells us they are 0 order for omega, right? And that also you can count due to these conditions of these parallel vectors. I mean, you add P1, 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 and here P1, there P1, and you can count that at each Pi. So the total angle is, indeed, this time it's 4 pi for each. So altogether it's still 8 pi. So that's good for the decagon. So 4 pi is 2 times 2 pi, right? So remember, this integer multiple is always 1 larger. So the extraneous, the actual copy corresponding to the vanishing order of omega. So because here is 2, that tells us the vanishing order of omega at Pi is 1, right? That tells us. So each Pi is really a simple 0 of omega. Or in other words, the associated 0 loci of omega counting with multiplicity is given by P1 plus P2. So this one form is different from the one in example 1. So it has 2 distinct zeros, but each is only a simple 0. So the original one has a unique 0, however, the vanishing order is 2. So they are very well reflected in the 2 different polygon presentations. Okay, so I still have 15 minutes for the first lecture. I sort of finished the introduction of these 2 objects. So, any questions?
some sense, this representation is unique because like if here you can construct the genus 2 with double P, but can you make something like identify 3 edges with something different shape? So
you can make it different shape, but the thing is, essentially after, maybe let me do it in this example. Suppose here I can maybe take this point. This point is also this point, right? I can somehow recut it. I split it into 2 parts. And then move this part to the other, so it becomes a sort of, in this picture it still looks like the same, but in general you can imagine, suppose I cut from here to there, I cut it, and split it, and just in this Euclidean plane, say just directly identify this edge with that edge. So you can, the right way to say that you have to consider these flat polygon pictures up to this cutting and pasting process. In other words, if you can start from one polygon this way and cut and paste to get another polygon, they correspond to isomorphic one forms. In other words, these underlying Riemann surfaces along with one form, they are isomorphic. They do not define like a new object. So like another way to present.
But is it known all same types are coming by this pasting and cutting?
I mean, usually the way to think of, I'll get to this a little bit later, but maybe for now is, so this is something I mentioned earlier to you. So these edges come from the so-called period coordinates. So they are not like globally canonical, they are only like local coordinates. You can certainly, for instance, if you define period coordinates, it's subject to a choice of basis in H1. So even for period coordinates, you can define differently. Yeah. So as far as I know, given one form, you can always find sort of a way to present it. But this way is not unique, because at least the period coordinates, the choice is not like unique, right? It's at least up to a choice of basis, and here is also maybe there's some further choice of cutting and paste. Yeah. For instance, I can even draw maybe in some cases a special sexagon to present a torus, but after new cutting and pasting, you will just get this picture. So just by looking at the polygon, it may trick you, but the right way to work out the special point and their one-shotter, that will essentially determine this information. This information is uniquely determined by omega or by the polygon. Any other questions? Okay, let's move to the next section. Well, so the next section is called, well, the thing is, so far we only determined a single translation surface and a single one form. So you know, if you study, like many subjects in mathematics, you want to study objects with similar structure in a family, usually called modular spaces, or like in down-to-earth term, like parameter spaces. For instance, you have a modular space for all Riemann surfaces of the same genus, right? I mean, similarly, we'd like to study some kind of modular space or parameter space parameterizing, say, flat polygons of same, say, gluing pattern or same topological type. So here I can, like, enlarging or shrinking or perturbing the shape of this polygon. But you see the number of edges, the gluing pattern, and the number of vertices preserved under this action. Right. But the geometry of this underlying Riemann surface and this one form may become different. Right. I'd like to take this into account to form a family. So in the literature, they are called strata of translation surfaces or abelian differentials or holonomial one forms. They're still the same. It's just like called strata of one forms. So in the literature, so people use some other name for one forms, also called abelian differential. It doesn't matter. So abelian differential. Just means holomorphic one form in our context. And this is only the starting point of story. The most interesting part in this subjects is coming from a special group action called GL2R action. I'll define it later. Acting on this parameter space of one forms. Okay, so that's the next topic. Well, let's start from this strata of one forms. Maybe after this definition, we'll take a 1 hour break, and we can do some free discussion if you want. So what we can do is to take one forms omega with a prescribed or given type of zeros, which means you fix the number of distinct zeros of omega along with their one-shot order. So in this case, for instance, we just want to look at omega on a genus 2 surface with 2 simple zeros. We take all of them into account. Or in the first example, we can consider omega on a genus 2 Riemann surface with double zeros, but we take all of them. So you see the information we need to be given before defining the strata is just some kind of like number of zeros along with their one order, but the total sum, again by this correspond A, or the degree of the canonical line bundle should be 2 times genus minus 2. So let's fix these coefficients summing up to 2g minus 2. So let's take, I call it a partition mu, which consisting of these coefficients for the zeros m1, m2 up to mn, a partition of 2g minus 2. So in this talk, G always refers to genus. So that means, so partition just means, so each entry mi is a positive integer, and the sum of mi is equal to 2g minus 2. Okay, so we fix this data. Yeah. You give me genus, and also you give me a collection of positive integers summing up to 2g minus 2. So let's define the following thing. So the notation I use curly h, just h, like fancy h, with respect to this given data mu, or this collection of integers m. So first, let me define it as a set. As a set, it parameterizes the following data. So it consists of a pair. So I need a Riemann surface, or surface x. Also, I need a one form omega on x. So I have x and omega. So here, x can be, in principle, an arbitrary Riemann surface of genus G. And omega is some one form on x, satisfying the condition. Let me write it down. So x is of genus G, a Riemann surface of genus G. And omega is a one form, holomorphic one form on x, so that the zero of omega is of the type given by mu. That is m1 p1 plus mn pn for some distinct point pi in x. Although here the pi's are not fixed. I'm just saying there exists a bunch of pi's satisfying this condition. That's okay. So I define it as a set consisting of Riemann surface of genus G admitting holomorphic one forms omega of this type. So these are somehow, so this depends on the collection of these n integers m1 up to mn. So I'll give you some examples maybe later today in the second talk. But before I finish, so in the remaining 5 minutes, let me introduce a couple more just notation. So first, this set H mu has a name. We call it the strata of one forms with signature mu. Right? So it is purely determined by mu. That's some remark. Okay, let me just continue here. These are definitions. So H mu is called the strata of one forms with signature mu. I mean, you can think of it also accordingly from the viewpoint of flat surfaces, right? So H mu is also the parameter space, or at least the set of like this flat polygon with, after gluing with n distinct special point, each point has total angle given by the Vansian order mi plus 1 times 2 pi. So that's another way to think of H mu, up to the cutting and pasting isomorphism. But this way, from one form is maybe more algebraic or like simpler to state. Just one thing. So let's take the union of all these H mu together. So far, H mu is only a single space, right? So what about if we consider dropping this condition, the zero type of omega, just parameterizing all Riemann surfaces of genus G along with all one forms on these Riemann surfaces? Then you will get a quite good object, maybe familiar to some of you. Just as a remark now, the union of all H mu. So here we still keep the genus, so given G. So let me write it. The union of H mu is given by, say, the union of H mu. And here mu is all partition of 2G minus 2. Let's give it a name. Just call it H, because now it's independent of the partition mu. Right? So what is this space? This is really like this is a space of all one forms, all possible genus G Riemann surfaces, right? Okay. Now this is good, because for the given Riemann surface of genus G, you know the space of one forms. That is a G-dimensional vector space. Right? It's a space of H naught of K. K is a canonical bundle of the cotangent line bundle of the Riemann surface. So this space, if you consider mapping to, let me use this notation, I'll come back to this maybe in the third talk. Mg, that is the modular space of genus G's Riemann surfaces. So far I say Riemann surfaces are always mean closed and smooth. So Mg is in general for genus bigger than 1 is a 3G minus 3 complex dimensional space. So it is not only a set, it has a very nice structure. And if you look at this relative viewpoint, so this map is given by dropping the one forms, only keeping the underlying surface. So this, the fiber of H over a Riemann surface, let's call it X, treated as a point parameterized by the modular space over X, is nothing but, as I said, the total space of one forms. And in the algebraic language, that's H naught of the canonical bundle of X. Right? So where Kx is a canonical bundle, line bundle. Okay, so this is a G-dimensional vector space, which tells us, although it could be mysterious to understanding the structure of each individual H mu, however, if you put them all together, then globally this actually forms, because we know the fiber is G-dimensional vector space altogether, this gives you sort of indicating a vector bundle of rank G over Mg. So they sort of intuitively tells us, not quite a proof, but intuitively tells us the total union H is a vector bundle. So there's a name for it called the Hodge bundle. It's a vector bundle of rank G over the modular space of G Riemann surfaces over MG. Well, I mean, more rigorous speaking, because so far we talk about one form only identically non-zero, but for the Hodge bundle, you could get everywhere zero one form. So you have to add the totally zero section to the Hodge bundle. That gives you the total Hodge bundle. All right, I think let me just maybe stop here for the first hour.